All right, so here we go. Oops. Okay, so center. Do you guys? What do you guys know about center of mass? Maybe that's a good place to start. Sure, what do you got, David? No, I know it's right. Like define this thing without using words, right? Perfect. That's a great way of saying it. It's the average position of the object's mass. That's a perfect way of saying it. Okay? Because the center of mass is exactly that. It's a position. All right? And the notation that we're going to use to indicate the center of mass is x for position, and then COM as in center of mass. Okay? So, there are going to be problems on the homework where you're going to be asked to find the center of mass. And I'm going to be looking for a position. Okay? The easy problems are just in one dimension. Sometimes they're 2 or 3 dimensions, and we'll talk about all of that. All right? A couple properties of center of mass. All right? So, if I throw a baseball, the baseball follows a parabolic path, right? Okay? But if you throw a hammer, the hammer like flips through the air. The path that it follows looks really complicated, right? Okay? But it turns out that the center of mass follows exactly the path that you think that it should, and the rest of the hammer kind of rotates about that center of mass. All right? So, the nice people at MIT made this little video to illustrate that. So, can I get somebody to kill the lights over there for me real quick? All right, so here we go. So what they're going to do in the video here, well, you can read. So, a badminton racket or something. I don't know what that is. Something with a big weight at the end. All right. So I think that was the badminton racket again, or maybe that the thing with the weight at the end. I don't know. But anyway, you can see what is the center of gravity doing? Yeah, it's following a nice parabolic path, exactly as you would expect it to, right? Okay. So when you're treating an object,
that guy seriously sucks at drawing.
Yeah.
Okay.
That's good. All right. Okay. So anyway. Okay. Okay. So the center of mass follows the parabolic path, just like you would expect it to. Other properties of the center of mass that are worth commenting on is this: that when you put a force on an object, sometimes that force will cause the object to rotate, right? We'll talk about that a little bit more when we do torque, right? Just what I'm doing with my understates, right? But like, so, if I put a force on this wheel, I can cause it to rotate, okay? It turns out, though, if you apply the force at the center of mass, it doesn't necessarily cause rotation, and the object will behave exactly the same as a particle located at that position, okay? In other words, the center of mass will follow the same path that a particle would follow if it had that same force at the same location. Okay? So, ultimately, I think what we need to focus on at this point is exactly what David said, which is that the center of mass represents the average position of the object's mass. All right? And so how do we find it? So, it depends on the scenario. So, if you're just looking at a number of particles, okay, so imagine that you had, I don't know that you need to draw this, but just listen for a minute. So suppose you've got, a particle here, and maybe this particle has a mass of, whatever, 2 kilograms. And then over here you've got another particle that has a mass of, let's say, 6 kilograms. Okay? If you wanted to find the center of mass of that system, you can do that. All right? And so the way that you do it is you set up a coordinate system, a number system. And you use this equation right here, okay? You multiply the mass of each of your particles by the position of those particles, and then divide it by the total mass, all right? So continuing with this example here, so what we would do is we'd have to set up a number line, okay? So for simplicity, let's call one of the ends 0. So let's call that a position is 0. All right, and then number from there. So I don't know, maybe it goes x equals 1, x equals 2, x equals 3, and maybe this guy is at a position of 4. And those are all in meters. All right, so for that example there, to find our center of mass, I'm just going to follow the equation there. So the position of our center of mass, and I'll do a more enlightening example in a minute, so bear with me here for a minute. So what I would do is I would take my first mass, 2 kilograms, and multiply it by the position of that particle, which is 0, right? And then add, let's see, mass 2, that's 6 kilograms, times its position, which is 4 meters, and then divide that by my total mass of 2 kilograms plus 6 kilograms. So what do we get? Let's see. 2 times 0 is 0, plus we get 24. Oops, whoa, what happened there? So you get 24 kilogram meters divided by 8 kilograms, and you get 3 meters. So what that's telling me is that my center of mass is right here. And that should make some intuitive sense, because notice it's closer to the heavier mass, right? Does that make sense, right? Like you've got more mass down here than you do here. So on average, there's more mass at higher position than closer to 0, right? All right. I'm not going to do it, but totally worth your while is do this again and pick another number line system. Like renumber these, call this a position of negative 12, and then negative 11, negative 10, negative 9, negative 8, and do the calculation again, and you'll find that the center of mass is still right here at that same location. You know, it'll have a different number because you've renumbered it, but it'll still be in the same spot. All right? So down here, it says, note, the choice of coordinate systems doesn't affect it. Okay? Does that make sense? All right, are there questions on what I just did there? Okay, so those are sort of like the most basic center of mass problems, all right? So the reason these are basic is because we're dealing with these as particles, but they sort of don't have size, they just have location, right? It's sort of like this infinitesimally small mass concentrated at that one point. But, you know, as we know, objects don't really work that way, right? Objects have size, okay? So how do you find the center of mass of an object as opposed to a particle? All right. Well, basically what you do is you repeat the process for all of the particles that make up the object. Oh, great. So what do so do I use the protons, right? Like that gets crazy complicated, right? Okay. Because, you know, basically for all intents and purposes, you're going to have kind of an infinite sum, right? So not an infinite number of particles, but a vast number of particles. So one way to do it is by taking an integral. And my original intent was to not worry about this, but I looked at the AP exam, and we do actually have to learn how to do these, all right? So we'll get to an example of an integral in a minute, but I don't want to start there, okay? All right? Most of the examples in the book are examples where you can use symmetry to find the center of mass, okay? So what we're going to do is we're going to use it for most problems. We're going to use a combination of just some kind of common sense symmetry combined with what we just learned. Okay, so let me show you an example of that first. How you can kind of use this idea of symmetry to find the center of mass. And then we'll talk about an example where you have to integrate to find the center of mass. Okay, questions before I go on? Okay, cool. So, all right, so suppose I give you a big figure like this. And I ask you to find the center of mass. All right. So a couple things worth noting here. First of all, now I need to find 2 center of mass positions. I need to find my x center of mass. Oops, not how you spell center of mass. And I need to find my y center of mass. Make sense? because there's going to be a center of mass horizontally and one vertically. One of them should be relatively obvious, though. Vertically, where should my center of mass be? At 0, right? Because it's symmetric about the horizontal axis, right? So my y center of mass is 0 just by symmetry, right? Follow? Now, to find the horizontal center of mass, first of all, what you can kind of do is you don't need to worry about where the object is vertically. All we're going to look at is the horizontal position of it. All right? So there are two ways of doing this. The first way to do it is what I'm going to call addition. All right? And the only reason I call it that is because the book shows a method called subtraction, and this seems like the obvious counterpart. All right? So what I'm going to do is I'm going to sort of imagine breaking this bar up into 3 particles, 3 discrete particles. All right? So that's going to be piece A. That's going to be piece B. That's going to be piece C. Good? So, horizontally, where is the center of mass for object A? Right? Horizontally, where is the center of mass of, well, let's jump to C since it's easy. Where's the center of mass of C? Also at 0, right? Because it's symmetric, right? All right, so the one that's, oh, I guess one tiny bit trickier is finding where's our position of B? Well, let's see. What are the horizontal dimensions of B? How long is B? 4D, right? So where would the center be? 2 from either end, right? Does that make sense? Right? So it's going to be right in the middle, right? So what's that position there? Negative 1D, right? Does that make sense? All right, so now I know, so now kind of what I can do is I can treat each of those chunks as a particle, right? Because I know where the center of mass of each of them is, so I'm going to just treat them as particles, located at their center of mass. Follow? But in order to do that, we need to know their mass. And we're not given any information about the mass. But we know this, and I've already used this. I probably should have said it explicitly earlier on. It tells you that it is uniform. So what do I mean when I say that it's uniform?
Every point has the same density.
Yeah, the density is uniform. So if you were to divide it up into chunks of equal size, each chunk would have the same mass, right? Huh. So let's divide it up into chunks. But we need them to be equal chunks, so they all have the same mass. So, I don't know about you, but I'm looking at this. I'm seeing it like chunk, 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 for a total of 8 chunks, right? Aren't those all equal size? Follow? So, here we go. So, oops, why do I keep doing that? Man, like COM is hard to spell. All right, so I'm going to do it's basically just that equation I did, right? X times m plus x times m plus x times m, all divided by the total mass. Follow? So, for chunk A, my x is at 0. What's the mass of chunk A? 3, right? So 3 units. Let's just call it 3 m's, right? Does that make sense? So each chunk has a mass m. Okay? Plus, let's see, chunk B has a position of -1, right? I was just going to do ABC.
The letter D, never mind.
I gotcha. Yes, we do have to have the letter D because it looks like D is 1 meter.
Yeah.
I see what you're saying. Yeah. Why did they do that? That's weird. 6D equals 6 meters? Yeah, I don't know. Okay, so I'm going to leave the D in. With that? Solve for D, right? Yeah. How many stops did the bus make? All right, what's my mass for chunk B? 2m. Plus chunk C is going to be the same as A, right? 0 times 3m, right? Do you guys see what I did there or no?
Yeah, we did.
Go ahead. Good. M is for mass, not meters. And the M represents the mass of like one of these little chunks.
That's not related to that.
Sorry?
That's not related to that. Under one.
That's 6 meters. This M is meters.
Okay. I just want to make sure that they weren't the same.
I got you. Okay. All right. Everybody good? All right. So I've done x times m plus x times m plus x times m. What goes on the bottom of the fraction?
8m.
The total mass, 8m, right? So technically it's 3m plus 2m plus 3m, just to be details. But so look what we get. On the top you get negative 2 dm, and on the bottom I've got 8m. So I'm going to get negative 1/4 d, right? So there's where my center of mass is. And since d is 1, that's just negative 1/4 of a meter.
All right.
We'll spell out meters to avoid confusion with the other end. Yes.
And we don't even include y and 0.
Oh, right, yeah. Well, I mean, we included it, but, you know, I sort of wrote it off to the side.
So is there any specific way we're supposed to like?
I guess I'd write it as an XY coordinate.
That's what I thought.
So, yeah, so final answer. Thank you for pushing me to do this. So, our center of mass is at the point negative 0.25 meters, right? A quarter of a meter, comma, 0 meters. Yeah, Marcus.
I like to try to do it less by saying like the whole thing is 32, so it has to be 16 on each side.
Wait, the whole thing is 32.
32.
Yeah, like I just really thought it was really
32 what?
I don't even know.
Are you talking mass units or area units or?
Like area, like area.
Okay, I guess area units and mass units are proportional.
Yeah.
So where did you get the? Oh, I see what you did. I see what you did. Your total area is 32d squared. Okay.
So you have to find the point where it's like 16 on both sides. So,
Oh,
and it's 14 on the 14 on the other side.
that does not work. And I don't mean that in a snarky way. Here's why. Here's why. It just on an intuitive level. Here's why it doesn't work. Check it out. Teeter totter. Little kid, big kid. Could that teeter totter balance?
Yes.
Yes. Do I have half of the mass on one side and half of the mass on the other? No, because the distance matters too. You haven't factored in the fact that it's not just the mass that matters, but where the mass is located that matters. Does that make sense?
Yeah.
So the mass particles that are farther away from your center of mass sort of weigh more. I don't mean weigh in terms of force of gravity. They count more, maybe is a better way to say it.
So if it was uniform with the solid square? I know, I'm saying it works because this one's uniform.
Oh, I see what you're saying. Correct. Correct.
Okay.
Oh jeez.
Yeah, and if it's not uniform, that's when we have to use integrals. And that's when it gets ugly. I know. Hooray, right? Thank you, AP Physics. Okay, so are we good with this? All right. So, so here's the other way. I don't know that the other way is any easier or harder. It's just a different way of thinking about it. I think that the value in the other way, the book does this example with, oh, well, it's in the notes. So, sometimes addition won't work because you'll have a weird shaped object. And you'll see an example of that in a second. So let me show you an alternative way of getting the same answer using a method called subtraction. All right? So what we're going to do here is this. Instead of picturing it as 8 little chunks, we're going to picture it as one big chunk, and then we're going to subtract out this little piece here.
All right.
Follow? Okay. So again, we can do the same thing we did before. What's the center of mass vertically? That's 0, right? Okay. Horizontally, all right, well, let's see. That's going to be, how do I want to say this? So there's the big square, and when I say the big square, I mean the big square, right? Where would the center of mass of that be? 0, right? So, so my position would be 0 times, what would the mass of that big square be? Keeping in mind that we're pretending that it's a solid square. There's no bit missing. What would the mass be?
36.
Sure, 36, or yeah, I mean, I'm kind of picturing it as 9 chunks, right? Like before we had 8, but now we've still got the extra ones. Like, I guess if you want to go 36, you can do that. It doesn't matter. 9 or 36, take your pick. I'm going to go with 9. So 9 mass units. Follow? All right. Plus, now, what's the mass of our missing bit? It's 1 mass unit, right? We're kind of missing 1 chunk, right? So it's got a mass of -1. You guys see what I'm saying, or no? Like the whole thing is a mass of 9m, but we got to subtract out 1m to get rid of this guy. Okay? So we just got to figure out the center of mass of that. So -1 mass unit for the piece we're subtracting. And where is the center of mass of that piece we're missing? Well, it would be right in the middle, right? So wouldn't that be in a position of, what, 2D? You guys see what I'm saying, or no? It's like, where's the center of mass of this thing? It's at 2, right? So 2D. Good? Follow? And then divided by your total mass, which is 9m plus -1m. So instead of adding 3 chunks that I had, I took 1 big chunk and then subtracted out the piece I was missing.
Why do we use,
Do you see why?
yeah.
Cool? And it gives you the same thing, right? Let's see, on the top you're going to get -2dm, on the bottom you get 8m, and you get -1/4d again. So we get the same answer, which makes us happy. Cool? Questions? Okay. All right, so why subtracting? Well, take a look at this shape here. They've got this disc with a disc cut out of the disc. There's no way you can do that by addition, right? Because there's no way you could sort of find, like, split this, you know, what color is this? We call it blue.
Teal.
Teal? I only work in the 8 Crayola colors, so if it's not in a box of 8 Crayola, that's what it is. All right, but if you guys tell me it's teal, wait, that's totally, wait. Whatever.
It's teal.
Teal. All right, so there is no way that you could sort of find the center of mass of that teal bit, you know, just by like breaking it up into little chunks and adding them together, right? So really the only way to do it is to find the center of mass of the whole teal bit and then subtract out the piece that you cut out. Follow? All right, this example is in your book. It's very, very similar to what we just did here, except they're circles instead of squares. I'm going to leave you to look that up in the book if you want, okay? It's the same exact process. Yes?
Just like how addition wouldn't work on here, is there a time where subtraction doesn't work?
Oh, that's a good question. Yeah, I mean, I guess if you had the reverse of this, if you had, you know, like 2 circles right next to each other, I don't know that it would make sense to do that by subtraction. You just add the 2 circles, right? So, good question. All right. Everybody good? Yeah. All right, so, oh no. What happened to my example that I added in? Oh. Shoot. my slides are out of order. How much time do we have? What do we got? 10 minutes? All right. Okay, so I'm going to jump. I jumped ahead a slide. I'm sorry. I added a slide this afternoon when I realized we had to learn how to do it by integration, and I apparently put the slide in the wrong spot. So we're jumping to this slide for a minute. All right. So, oh shoot, I was going to do this thing with the error. Not enough time. Sorry, I'm processing if I want to show you this example that I set up over here, but I think we're good. Are you guys okay with the uniform density thing and compacting it down to a point? And...
Yeah.
Okay, all right. Okay, so integral. All right, so what if the object isn't symmetrical? So picture a baseball bat. All right? So you know that the center of mass on a baseball bat is going to lie somewhere, like, I'm going to make a bad drawing, so bear with me for a minute. There you go.
It's like those plastic ones you use in gym class.
All right. So here's my baseball bat, right? So I know because there are 3 axes, right?
Yeah.
It's symmetric about 2 of them, right? So I know that my center of mass is going to be somewhere along a line that runs down the middle, right? Okay? So really what I can do is I can treat this as a rod with varying density, right? Like it's sort of more dense at this end because there's more matter. All right? And what that's called is it's called linear density. All right? It's the amount of mass contained in, a small linear distance. Follow? Okay? So it's usually indicated by the Greek letter lambda. Linear density. All right? And it's the change in mass per unit change in x. So if you divide this up into little chunks, it's what the mass of a little, chunk would be. All right, but the problem is it's not uniform, right? Hello? All right, so what we're going to do is basically the bat gets fatter as it goes out to the end, right?
Yeah.
All right, so let's do this. Suppose we had a scenario, or scenario if you prefer. No? Okay, that's fine. So, position, density. All right, so in this example, here's our equation for linear density. Our linear density here is 0.125 times x. So this is it's a line, right? So basically, here's my density. It's just a line that looks like that, right? And if you imagine rotating that around, it's going to kind of give you a cone, right? Does that make sense?
Yeah.
So if you simplify a baseball bat into a long, skinny cone, that's kind of what this would give you. Follow?
Yeah.
Yeah, Marcus.
Wait, so what are we using for this? Are we using that
No, the bat I was just showing you that that's an example of a thing where your density is not uniform.
It's this rod.
But I guess what I'm saying is you could treat a baseball bat as a rod of varying density. Good? I think we're okay. So maybe what's tangling you up is when you picture a rod, you picture a cylinder, right? Okay. So the reason the baseball bat is heavier at one end is because it's fatter. All right. So let's pretend that we took that fatness and squished it and just made it more dense, so that it became a uniform rod. You know what I mean? So it would have to be, maybe this end is wood, and then in the middle it's styrofoam, and then at the end it's metal of some sort. You know what I mean?
I thought we were going to say that there's more density in that header, it's just that.
Okay, right. So you guys, for this, remember, when we talk about linear density, you're right. The density of the bat, like if you do mass per unit volume, it's more or less uniform because it's all wood, right? But we're not talking volume density, we're talking linear density. Do you understand the distinction between those? Exactly. It's if you broke it up into like 1-inch chunks. What's the mass of this inch? What's the mass of this inch? Right, and yeah. Good, you guys? Okay, so this is going to be some some calculus, all right? So here's how you find the center of mass. It's basically the same summation that we just did, but it's written as an integral, all right? So to find the position of the center of mass, you integrate the position of your mass, okay? And then you divide it by your total mass, all right? Now, a lot of times you won't know the total mass, and so the easiest way to find the total mass is to integrate with respect to mass.
Integrate what?
1. So check it out. So here, literally, you're integrating 1. All right. So this is the function 1. It's a function of mass. Okay. So the function is always 1, no matter what your mass is. So if I take the integral of this curve, my area is going to be the total mass times 1, right? And so that's going to give you m again, right? Okay? Oh. What's wrong? Are we good? Why does this hate me? Say it again, Patrick. You sure? No. How do I want to say this? So what I'm saying is, so to find m, here, this is going to be silly. Check it out. Look. That's a true statement. Convince yourself of it. So this is the same as the integral from 0 to 4 of 1 times dx. Oh, sorry. So this is not calculus, this is physics. Sorry, this is not physics, this is calculus. All right, so what's the integral of 1? X, right? So this is x evaluated between 0 and 4, right? So you just do 4 minus 0. Good? So that's what this is doing. You're integrating your mass with your endpoints. I guess your endpoints would have to go from 0 to m, capital M.
Okay.
Bear with me. You'll see why we're doing this in a minute. Except that we don't have it yet, do we? All right. So here's the trick. And it's always weird to me that these integrals are written so that you're integrating with respect to the mass. That seems really counterintuitive and awkward to me. And so what you need to do is you need to rewrite these integrals. You need to do what's called substitution of variables. And rewrite it so that the integrals are dx instead of dm. So here's the deal. I know that the definition of linear density is change in mass per change in position, right? It's how much a little chunk of it, what the mass of a little horizontal chunk is, right? Does that make sense? Okay, so multiply both sides by dx, and you find that dm is lambda dx. Now, you can write this down, you guys, every single one of these problems that has a non-uniform density, you're always going to do this. They all work the same way. All right? And so now what I can do is I can replace lambda with my expression for lambda. So that means that dm is, oh, well, look, lambda is 0.125x, so that's my lambda, times dx, right? Follow?
Wait, so what's dx and dm?
Say that again.
What are dx and dm?
Like, what do they mean?
Yeah,
Dx is
it's tiny changes.
a tiny change in position, like a tiny chunk of the thing, and dm is how much extra mass you gain because of that extra chunk.
Okay. Okay.
Good. The d's they're like like dx, dm, it's the same as delta, but it just means very, very small. Okay? So, our integral, which we're not going to have time to do this right now, we'll have to finish up tomorrow, but so our integral then becomes the integral of x dm. Well, here's dm, right? So the integral of x dm is the integral of x times 0.125x dx. Follow? And the bottom of the fraction is the integral of dm, which is the integral of 0.125x dx. Does this make sense or no? All right, now, the last thing, and we'll have to finish the math up tomorrow. I'll save this and we'll pick up here tomorrow. So in order to integrate, we need to know our bounds, right? Well, look, now our integration is with respect to x. So if you read the problem, it says, imagine a thin rod of length 0.75 meters. So where do I want to integrate from? From 0 to 0.75. And then solve that. And that gives you your position. Right? We'll do the actual integral tomorrow. You guys can probably do the first few homework problems. We'll talk more tomorrow about what to do when. Oh, why did I record that today? Everybody was here.
I was really gonna say,
I did record it.
you did all.